Hello and welcome to the UTA Virtual Innovation Day. We're the pioneers with Aaron, Anne, Nosisa, and our mentor, Dr. Yetkin. We present a wearable American Sign Language translation device. Our lightweight gesture-based interface device concept comprises 5 rings that are wired to a wrist wearable and 5 wireless fingernail-attached devices. The intended application of the device is translation of American Sign Language and other trained sign languages. Our American Sign Language translator uses a novel optical recognition paradigm that determines gesture by emitting and receiving infrared signals between each other to measure proximity through signal intensity coming from each LED, which is unique to each finger. The current system has audio output and recognizes 8 sign letters, and the system is controlled by buttons to train the neural network, predict, and default and user can retrain the device without any external help. The design process therefore includes fabricating devices for input and attaching speaker for output, and with the addition of buttons, the device can be trained for data. There are some different models of translators in development, and they mainly fall into 2 designs. Majority of them use camera-based interfaces, capturing gesture, and others use glove equipped with sensors. These 2 models include computer usage to capture, record, and match gestures to previously learned word or phrase. Our system is hand movement and use built-in processor to translate rather than using deep learning-based technology and AI to process natural language algorithms, which is common in camera and computer-based translators. And this is our overall system. We can see the fingernails, the rings, and the wrist wearable contains Arduino Mega, Raspberry Pi, integration board, speaker, and battery.
To start off, we began by identifying some specifications we wanted to implement in the previously designed ring and fingernail devices, and then came up with additional features so that our device would be portable, operated headlessly, and would predict 24 of the 26 ASL alphabet letters and give a visual output of those letters in under 500 milliseconds. The issue with our design process was being able to design such a device on a $300 budget and adhering to the COVID-19 safety protocols, but we were able to do so. And to test our device's functionality, we ran some hardware and software tests, such as the device's ability to call on the respective Python code when pressed.
Our device starts by having the Arduino Mega light up each IR LED in the rings for 50 milliseconds sequentially. This signal will trigger the power gating chip in the fingernails to turn on the infrared LEDs in those devices. All infrared signals will be read by the infrared receivers in the rings, and the Arduino will output a 15 by 25 matrix or 15 by 15 matrix if only the rings are being used, as seen in Figure 5. Each value in the matrix will signify the proximity of the LED to the sensor. This matrix will be used for gesture prediction or training of the neural network in the Pi, depending on the button input.
Currently, 8 letters have been trained. The device is 92% accurate and 100% repeatable, which we determined after testing the device under various conditions. It gives a visual output of the signed letter in 500 milliseconds, and when connected to a 10,000 mAh power bank, it can last up to 4 hours. 5 buttons and status LEDs have been connected, as demonstrated by Figure 6. Button 1 allows the user to predict the sign gesture. Button 2 resets the device to default settings in case a mistake happens. Buttons 3 and 4 allow the user to train the device to recognize the sign gesture, and button 5 reboots the device. Proper training of the letters allows the device to successfully predict the sign gesture. Figure 7 shows the results obtained when we tested the ring's ability to detect infrared light changes, and the middle ring was faulty as shown by the lack of signal, and therefore it has to be fabricated again. Here's a demonstration of our device predicting some letters.
U T A.
We believe our device meets many of the set goal specifications and constraints by translating certain gestures as a self-contained system and creating an audio output. In the future, we hope to manufacture new ring devices with a more optically clear material to successfully trigger and incorporate the fingernail devices. We also hope to add a screen and add a smaller Raspberry Pi.